Okay, so hello everyone, my name is Stephanie Gonzalez. Today I'll be
Hello, Stephanie. Somehow I think your audio is become very, unclear. Can you maybe turn the volume up? Yeah, I cannot hear you.
Okay, does it sound better now?
Yeah, a little bit better, but still very small. Yeah, can you maybe turn to the maximum?
Okay, like this?
Yeah, I think that's better.
Okay. So yeah, the research paper I researched was the way to my heart is through contrastive learning, remote photoseismography from unlabeled video. My name is Stephanie Gonzalez, and the researchers from this paper were John Gideon and Simon Stent, and this was done by the Toyota Research Institute in Cambridge, Massachusetts. I'm not sure how to change this slide. It's not really.
Yeah, you're not able to move to the next slide?
No, I think it's kind of slow.
Yeah, I think, yeah, it's working now. Okay. Good.
Okay, we went over a couple. Okay, sorry about that. So this research paper introduces a new approach to remote photoseismography, or RPPG, which is a technique in which changes in transmitted or reflected light from the body due to volumetric changes in blood flow are measured at a distance using a standard imaging device. In short, our PPG is the measurement of blood volume changes from observations of a person's face or skin. Our PPG relies on a signal to detect and estimate underlying cardiac activity, even from webcam quality videos. This means it is readily available for use and could meet the needs for low cost, non contact health monitoring. So this approach applies neural networks to learn deep representations of invariance to nuisance image variation and employs a fully self-supervised training approach. It also incorporates a learning saliency resampling module into both the unsupervised approach and supervised baseline. This shows that by allowing the model to learn where to sample the input image, it reduces the need for manually selected features and provides interpretation into the model's behavior. This contrasted training approach is built around three assumptions about the underlying signal of interest. The first assumption is that the signal lies within a certain range. This range is set to 40 to 250 beats per minute, which captures the vast majority of human heart rates. The next assumption is that the signal does not vary rapidly over short time intervals. And lastly, it is assumed that the signal has some visible manifestation, even if it is undetectable from the human eye. And it assumes that it is a dominant visual signal as well. So with these conditions met, it is possible to train a deep neural network to estimate the PPG signal of a subject from solely video of their face and entirely without ground truth training data. So this image shows a real output of the model trained on the UBFC dataset. I'll go over this dataset more in a later section, but as we can see from video of a person's face alone, the model learns to estimate the person's cardiac activity from PPF signal, which is shown over here, a PPG signal, and as well as the saliency signal, which is shown here. So this shows where the subject's estimated activity is the strongest. And in this case, as we can see from the output here, the signal is the strongest in the center of the forehead, which is why it is enlarged to showcase the strength of this signal. And we can also see that because of the byproduct of the saliency-based sampling model, the model can also output interpretable saliency maps, which provide some transparency into the spatial location of the model's signal of interest. And that is shown here by this highlighted area. So the motivation for this research is that the detection of the physiological changes of a person is important in areas of health, fitness, and human resource management. Contact PPG requires interpretation of the subject, and it is also difficult to set up. So advances in computer vision and machine learning have made RPPG possible for human health monitoring. And as I mentioned earlier, it is also a low-cost solution, so it's able to be readily available almost anywhere. So next, I'm going to go over the method of that the researchers have used. So first, I'm going to go over the pre-processing stage, and this stage minimizes nuisance variation and discards irrelevant information in the input data. This stage also estimates a bounding box around the subject face and uses an additional 50% added as a scaled buffer to the box before extracting a 192 by 128 frame. The buffered bounding box location on subsequent frames is only updated if the new non-buffered bounding box is located outside of the larger one. And the reason for this process is that it allows for relative stability of the video and allows occasional movement and realignment without negatively impacting the results. And at the last pre-processing stage, the videos are also cropped and scaled to a 64 by 64 resolution to finally be used as input for the model. And this resolution allows for a lower computational cost as well. Next step is the saliency sampler, and this step is, it consists of input video sequences which are passed to an optional saliency sampler module, which provides transparency as to what the PPG estimator is learning. And it is particularly valuable if little annotated data exists to validate with. And secondly, it aims to warp the input image to spatially emphasize task salient regions before passing it to the PPG estimator. And we can also note that the performance is only altered by at most 1 point, so it's not especially efficient for the performance. Next step is the PPG estimator. So as the PPG estimator, the model uses a modified version of the 3D CNN-based FISNet architecture. And this is a series of 8 3D convolutions and has 64 channels and ELU activation. This allows for the network to learn spatial temporal features over the input video, and average pooling and batch normalization are also employed between layers. Adapted averaging pooling is used to collapse the spatial dimension and produce a one-dimensional signal. A final 1D convolution is applied to convert the 64 channels to the output single channel PPG. Next, I'm going to go over the loss functions. The first one is a maximum cross correlation, or MSC, or MCC, and this is used to propose as a metric for RPPG supervised training. It determines the correlation at the ideal offset between signals and produces robustness for random temporal offsets in the ground truth under the assumption that the heart rate is stable. And the MCC is scaled by a constant which is determined by the ratio of the power inside the heart rate's frequencies, and it is necessary to ensure it remains unaffected by the frequency outside the relevant range. There's also multi-view triplet loss, or MVTL, and this is the loss function used for contrastive training. This enforces that the heart rate is relatively stable within a certain window and ensures that the signal within each view appears similar. Next, there is power spectral density mean squared error, or PCD-MSE, and it is performing contrastive training. This is on the frequency just of the first assumption we made earlier. The MSE is computed by normalizing each to have a sum of 1. Lastly, there's relevant power ratio, or IPR, and it is used as a validation metric during contrastive training. In this case, the PSD is calculated and split into the relevant and irrelevant frequencies, then divided by the irrelevant range with the total power. This is used as an unsupervised measure of signal quality. And I have this figure here that kind of summarizes all of the loss functions, the assumptions made for each, and what they're actually used by. Next, I'm going to go over the training and the steps involved. First, the researchers underwent sampling, and in the experiments, the researchers randomly sample 10 seconds from each video and its associated physiological ground truth. The training sets are randomly augmented by artificially stretching shorter video clips to 10 seconds using trilinear interpolation. Linear interpolation is used to mimic the stretching in the ground truth PPG and scale ground truth heart rate appropriately. Next step is heart rate calculation. So for some given PPG, they calculate the heart rate by zero padding the PPG signal for higher frequency precision and calculate the PSD. The frequency with the maximum magnitude within the relevant heart rate range is then calculated. And this method is used to calculate the missing heart rate ground truth and the heart rate from the predicted PPG. Next, it undergoes a saliency sampler, and again, this is optional. And if it is enabled, the input video is passed through this step, and the output can then be used to verify the performance of the network. Next, there's supervised training, and for this training step, the input video clip is passed through the PPG estimate and produces a PPG estimate value, which is then applied to the selected supervised loss function. And finally, for contrastive training, a resampling factor between 66% and 80% is randomly chosen, and the anchor video clip is passed through the trilinear resampler to produce the negative sample. So this increases the frequency of the heart rate by a factor of 1.25 to 1.5. And this frequency should match the output from the PPG estimated result. And this contrastive loss function is applied to the PSD MSE distances. And additionally, it's important to note that the models are implemented with PyTorch, and they're trained on a single NVIDIA Tesla V100 GPU, and a batch size of 4 for all experiments is used. Next, I'm going to go over the data sets. So the model is evaluated on 4 publicly available RPPG datasets from recent literature, and it has been adjusted into a common data format for available use to other researchers. The datasets chosen show that they're comparable or produce even better results when compared to recent supervised deep learning methods, but without the use of any annotation. The first dataset is called Pure, and this consists of 10 subjects performing different controlled head motions in front of the camera for about 1 minute per sequence under natural lighting. And for each sequence, the uncompressed images of the head and the reference PPG and heart rate from a single clip pulse oximeter were also recorded. So this data set also contains predefined folds for training, validation tests, and so it was used as a comparison to related work. The next data set used was COH face, and this data set has 161-minute videos from 40 different subjects, and it has a lower quality than pure. So the videos can potentially cause corruption of the RPPG signal because they are heavily compressed with a MPEG for visual. So we'll see later in the results how the quality affected the results of the experiments as well. And the next data set is MR-NIRP CAR, and this data set has ground truth pulse signals captured during driving, and the data was captured simultaneously in RGB and near infrared with associated pulse oximeter recordings as well. And it contains 190 videos of 19 subjects that were captured while driving, or they could also have been parked inside of a garage in their car. And the subjects performed different motion tasks such as talking, laughing, and looking around. The last data set used was UBFC. And this data set contained uncompressed videos from 43 subjects with ground truth, PPG, and heart rate data from a pulse oximeter. By engaging participants in a time-sensitive mathematical puzzle, the heart rate variation was introduced in this data set, and subjects with erroneous heart rate data were discarded for this experiment. And each of these data sets were analyzed for the amount of variation in heart rate, since this model makes the assumption that the heart rate does not vary over short time intervals. So it was found that the heart rate did not vary by more than 2.5 BPM in the majority of data over a 10-second window. Next, I'm going to go over the experiments for each of the data sets and the results that the researchers found. So for each experiment, the RMSE MAE and Pearson's correlation, or PC, was calculated for the predicted versus ground truth heart rate, and each experiment was run 25 times for stability. So in pure, the results for the data set were between a 2.4 to 3.0 RMSE, and these strong results were likely due to the high quality video that I mentioned earlier, and minimal movement of the subjects could have also played a part in these results. The contrastive method was also able to achieve similar results without the use of ground truth data. For COH face, the contrastive system performed best on this data set, as it had a RMSE of 4.6, despite not using labels during training. So this proved that the model is more robust to video compression in comparison to other methods. However, the supervised model performed worse with an RMSE of 7.8, but it outperformed the strongest comparable baseline of 10.9 RMSE. For MR-NIRP CAR dataset, this produces a low baseline of 2.9 RMSE, but the supervised system improves the result to 1.6 RMSE. The contrastive system performs the worst in this dataset with an RMSE of 4.1, but it does so without ground truth labels. For UBFC, the dataset compares against the 7.4 RMSE baseline, but it's not perfectly comparable because it uses the first 2 seconds of all samples for adaptation. So the RMSE scores for supervised and contrastive methods are 4.9 and 4.6 respectively, so they do have similar performance. So in this image, this is an example of interpretable model behavior. A random flashing point highlighted in red over here was added at a rate of 60 to 180 BPM, and it was trained on both the contrastive model and supervised model. In the contrastive model over here, we can see that without the need for ground truth data, the saliency map reveals that the model learned from the noise signal inside of the signal of interest on the subject. So the supervised model, in contrast, shows that the saliency sampler learned to emphasize the skin of the subject, and it also ignores the injected noise signal after resampling. This is because the noise signal had no relevance to the predictability of PPG. So that's why the forehead is enlarged here, and it's a lot smaller here because it's so focused on the noise in the contrastive model. So in conclusion, this research paper aims to estimate cardiac activity in a person from video of their face. The proposal presents the first time that deep neural networks have been applied to remote photophotosmography in a fully supervised manner with zero annotation costs. And this allows the heart rate detection to adapt to a specific domain without access to labeled data in the domain. The researchers also proposed the use of saliency sampler to provide interpretable output to confirm whether the system is behaving as expected. That concludes my presentation. Are there any questions for me?
Okay, yeah, thank you, Stephanie, for the presentation. So before go to the question, let me first give you a couple of comments regarding your presentation. So I think you understand the paper, some of the details, right? So each part you can explain very well, but I feel like your presentation slides is overly simplified. There's a lot of details are missing, especially during like a couple of slides. They're just very brief information, like data set, and you spend a lot of time, just reading or talking, explaining what is going on, but you didn't show much of the detail. So I was staring at those slices, trying to listen to the words, you talk, but it's very difficult to grasp what's going on, right? Some of the detailed information I can easily lost. So my suggestion for you is, I think you probably will do a better job for your final project presentation, is that put those detailed information in there and use animation. Okay. So for example, when you talk about the sampling, a couple of pre-processing steps, right? Sampling. So maybe talk one by one, right? Don't put everything in just one slide, right? So you can using maybe 2 or 3 slides to show each of the step, what's really going on, right? First is sampling, then you can show like a figure or maybe writing some of the keywords to summarize what is their key steps to do the sampling and do the interpolation or do some of the normalization, whatever. So you just have like a one slide with very simple keyword, then you explain by words. But for audience to understand that, we tried very hard to listen to every word you have, but it's very difficult to catch all those detailed information because just a lot of information going on, right? But if you also provide some of the visual aid, right? Put those important words in the slides or information in the slides, figure, whatever table, I think that will be much helpful. Okay, and also like the data set, right? So you have those 4 data set. You just put the name, but you spend like maybe 2 or 3 minutes explaining all these different data sets, some of statistics. So, for me, I couldn't, get that much information. So out there, but it's just too hard to focus on, get everything. So it's better to put those details in the slides, right? You have a table, you can actually like crop or take a screenshot of the tables, whatever the information there, and put in your slides. So this will be very useful to know what's exactly going on. The same thing for the experiments, right? Do they do any comparison, how they justify, do some ablation for each of the step they have, right? Specifically, they have those multiple losses, right? self-supervised contrast, using contrast learning, supervised, and maybe other losses, like what's their contribution, to the final performance for those individual components, right? So they must have these kind of analysis, show some comparisons, and also compare their method with other existing method, which I didn't see that in your presentation. So I think that's I feel that's the one weakness of the presentation. Yeah, I think if you are able to present all, adding more information to the slides, I think that would be very helpful. I know you understand all these details, and you explain that to us, but without all these kind of visual aids, it's quite difficult to take all those information in, right? Just listening to your explanation. Okay, so do you understand what I'm talking about?
Yeah, thank you for the feedback.
Yeah. Okay. So I think this will help you, if you do the final project presentation. So be mindful, the student may not, know the topic you are doing, right? Some of the detail is better to show that in the slides. And it also can help you to explain, right? So, using the animation one by one, right? You know what's to explain next, right? Present based on the information you present on the slide. Okay. So I didn't fully understand the paper, so I think you don't have those information in the slide. So for us to fully understand, could you please maybe pull out the paper you actually review, so maybe we can quickly go through and understand some of the component.
Okay. I believe there was part. Wait. Yeah, this one.
Yeah. Okay. So so first of all, the problem is basically estimate these PPG signal and the heart rate, right? So this what is this PPG signal, like cardio signals, and then you can estimate the heart rate from the PPG?
Yeah, that's correct.
So can I say this PPG is close to ECG signal, or they like similar to ECG signal, or maybe different?
In a way, I guess you can make that comparison, yeah.
Okay, so yeah, based on this graph illustration, so kind of like ECG signal, then you can estimate like a heart rate from that, right?
Professor, can I add something to that PPG signal?
Yeah, please go ahead.
Like that PPG signal is basically more of an optical measurement for measuring that blood circulation. And same as the one that we are talking about is the ECG one, is both are of similar nature, which is basically to determine a patient's heart rate and that graph, but one is done with electrodes and one is done with photodiodes.
Yeah.
So that's the basic difference out there, which I read before.
Yeah.
Like attending this.
Yeah. So yeah, I know the PPG is estimated from like images or videos. So basically you were trying to mimic the ECG, right? Because we know ECG, you have to wear those sensors attached to your body, right? Maybe a little bit intrusive.
Yes.
Of course, that can be, that is the ground truth, right? So that is more accurate than PPG estimate from the video.
Yes.
So based on your explanation, so PPG is basically trying to, get as close prediction, trying to mimic the ECG signal, right?
Yes, in a more non-invasive way. Yes.
Yeah. Okay, great. Yeah, thank you for the clarification. Okay. So Stanley, can you please go down, like, what is their approach, right? So how we know the input is a video, right? They're using 3D CNN to extract some features and eventually output like a 1D signal. So do they have like a diagram showing like what is the overall architecture they are doing?
Yeah, this diagram.
Yeah, okay. Yeah, I think, yeah, you probably should put this framework in the slide. So, and based on this, you can explain like what is the overview, right? What is the general idea of their approach, right? So you have this input, you have this kind of output, then you have different loss function and maybe perform some other functionality. Okay. So here they so can you explain like what is the sampling doing here?
Well, there's two different samples. There's the saliency sampler and then the frequency resampler. So this takes the input image and it goes through this optional step. Then it will go through the frequency resampler and then go through the PPG estimator where it'll actually make the estimations for the changes in blood volume, and then that will eventually produce this output image, which will showcase, for example, here in the subjects area where the PPG estimator was actually resolved.
Mm-hmm. So what is XAS? These they said this is generate a warped anchor. I see the video seems to be distorted, right, as compared to original input. So why do they do this kind of saliency sampler and generate this kind of distorted version of the input XAS? They are trying to magnify some of the part.
Yeah, it's done to make the interpretation of the results easier. So by enlarging, for example, the center of the forehead here, it's able to showcase where the signal was the strongest. So that's why it enlarges it. It is an optional step, but it does help to interpret the results.
Okay. Yeah, so it seems like they kind of magnify the forehead region. I don't know if that's maybe because of there's like a flat region, a lot of blood flow. Maybe it is, easier to identify some of the nuance changes reflected by the images or video frames. Okay. And so and can you also explain the loss? Like what is the contrastive loss doing here?
Right, it does go through this step, and the contrastive loss. I don't remember. I did go through this part, but there were different loss functions used. So are you asking for about like one specific?
Okay. Okay. So what about the supervised? What is the supervised loss mean here? Do they have a ground truth?
I don't remember actually. Because it did have like a separate section for the loss functions, but it goes through about 4 different ones. And I know that for unsupervised, it uses the IPR one, but I don't remember off the top of my head what the one for supervised was.
Yeah, so here, if you, it's okay. You can just look at the caption, right? If you don't remember, you can read it and maybe refresh your memory. So in the caption, it says, the anchor is passed through the PPG estimator to get YA, right? And employ a maximum cross correlation loss between the ground truths, YA tilde and YA, right? So the YA tilde is the ground truth. and YA is the estimation, right? So that's the supervised version, supervised part, right? Then they're using the contrastive learning, maybe to address some of the difficult cases, or maybe just adding this contrastive loss term to help the network learning. Okay. Can you also go to the result part? Okay, so do they compare with any existing methods? Because you didn't mention this in the slides.
Right, they don't, in this section, there is one up here where it kind of does
Oh,
talk
I think
about
in the table, later table.
Yeah, I'm just saying like they only discuss it up here, but not later on in the experiment results.
They didn't put it in the result.
I didn't notice
Can
it.
you look
No.
at the table? Let's see. Yeah, they have the compare with other method, right? I think in the upper part, those quantitative result. Yeah, so yeah,
There's a different data sets to use. It's not comparing it to other methods.
No, what about 1624, right? So those are the existing approach, right?
Where is that?
Table 3, like 30, 24, 16, those references showing green. HRCN,
Of these? Okay.
yeah, Meta RPPG. So these are the existing methods. That's what I'm talking about. How about table 2? Go to
These are showing the different data sets, but they didn't use all of these.
okay. So yeah, can you go down like table? Let's look at table 3. And is there any other table?
No.
Okay. Yeah, it seems like they didn't compare with many existing method. I don't know if it's because of, in this domain, there's a lack of existing methods. So maybe these are the most relevant they can found to do the comparison. So I think when you read this paper, these are the questions you may ask yourself, right? So for a high quality paper, we are looking for very thorough or comprehensive comparison, right? So if you look at this table, I would first questioning like, are these the state of the art method or the recent method they compare against, or they just didn't include some of the relevant or recent state of the art method for the comparison, right? So these are some of the questions you should think about and see if this is, you can justify, right? If they are do the fair comparison. So that's one thing you can think about. Okay. All right. So do you guys have any questions for Stephanie about this method and the topic?
I guess I have one.
Yeah.
Can you? Yeah. So I was just wondering what exactly does the self-supervised method actually train on? Is it just raw video data, or is there, and then later trained on the other metrics to get like an accurate prediction, or what exactly is it being initially trained on in the self-supervised learning part, I guess, is my question.
Yeah.
It does.
So yeah, Stephanie, please go ahead. Yeah.
It does kind of rely on the metrics that are provided, but they did showcase that the results aren't always the same. As we can see in this figure here, that it doesn't produce the best results. So they were mostly focused on the supervised model results because of that. So they didn't really dwell much on that because it was more used as like a comparison that the supervised model was the best approach.
Okay. But just in terms of being pushed, like the data that's passed into the self-supervised learning model, is it also EPPG or whatever the metric is? Are they also sending that data in as well to be self-supervised, learned on its own, or is it just video? If that question makes any sense.
I would say it's a bit of both.
Okay. Okay, thank you.
Yeah, so I don't know like what exactly going on for this contrastive model. So probably have to read the paper. Yeah, can you go to the framework? Let's maybe take a look again. So Stephanie, can you go to the framework?
This one?
Yeah.
So it says here a random frequency ratio is sampled from a prior distribution.
Yeah, so if you guys look at so typically they so if you look at those blue box, right? So they have the PPG estimator, right? So that's the G theta, right? So that's their network to estimate the PPG signal. So going into this blue box, there's two input, right? XAS and XNS, right? So the XNS is coming from XAS doing this kind of R, which is frequency resampler, okay? Yeah, based on the figure on the left, it seems like, in the upper XAS, maybe higher frequency, right? You see more frames, but XNS, maybe like a downsampled version of the input. So these two go through the PPG estimator, get YA and a YN, right? So YA and YN has the feature of FA and FN. So for those, we're going to be pushed far away, which means they may, so these, because the YN is coming from X and S, they have different, corresponding to different frames. Okay, so maybe different frequency. I don't know the details, but for my first guess is that because of the frequency resampler, okay, somehow their PPG signal should be different, okay, because of the frequency. So that's why you want to push them away, right? FA and FN, there's a red arrow, right? Push, right? But if you look at a YN, keep going through R, that's like R inverse, maybe do some inversion back to the same frequency range, right? So you get the YP, okay? So YP get the feature of FP, FA and FP should be pulled together close to each other, right? Which means they should have similar or the same PPG signals, okay? So that's the contrastive loss, right? So yeah, we talk about this contrastive learning, right? So you have from the same image, you do some augmentation, then that's the positive, right? You should put pull them together. But for a different image, they are considered negative pair. You should push them away. Okay, so in their case, how do they do the augmentation? They throw this kind of frequency resampler, right? Maybe based on the frequency, as a metric to determine if this is a positive pair or negative pair, right? Then you can using contrast loss to kind of constrain the learning problem. Okay, so I hope this can clarify a little bit. Okay, does that help? Okay, all right. So is there any other questions?
I had a question.
Yeah, go ahead.
So I know they trained their model on the 4 different data sets. Is it feasible for them to have combined the data sets in order to make a more robust, like generalizable predictor?
Yeah, I guess that's a yeah, that's a very good question. And I think it's possible, right? So you can using different data set. Of course, each data set has some of the ground truths for the training. So you can definitely combine these multiple data set as a generic, a large scale data set for the pre-training. And then you can, because, different data set maybe have different, there's, including all these kind of diversities, right? So maybe your model is able to generalize well, right? So in this case, then once your model is trained, then you can directly apply this model on all these, test set from these different data set. Then you don't have to train like individual models for each of the data set. Yeah. So yeah, actually for not just for this problem, a lot of other problems people doing this, right? If you you don't have enough data, right? But some of the data set, do have some similarities and share, the same task. You can combine the data set to form a larger one and do some pre-training or do some training on this large scale data set that could, potentially improve the generalization capability. Yeah.
Okay, awesome. That makes sense.
Yeah. Okay. Great. So I think this is a very good topic. So if you guys are interested, I actually there's some researcher from MIT. They using this kind of technique, using videos, put on observing some of the infant or maybe some of the early born baby in the ICU. They're using cameras because to estimate heart rate, to monitoring, because those babies maybe not very it's maybe not easy to attach a lot of sensors on infants, right? So they want some non-intrusive method. So they're using the cameras and taking the videos of the face region, and because of the blood flow, right? Breathe, inhale, hail. So those kind of blood flow will make some changes reflect in terms of color. So you can do some frequency analysis, do some Fourier transform and see how the frequency change or whatever. So then you are able to estimate like the breathe rate or heart rate. So I think this is pretty interesting. And also there's some apps, right? You have a phone, right? You can put your finger on the camera, you turn on the flashlight. Okay, so you put your finger on those flashlight, right? So, and you can actually measure how the blood flow change on your fingertip, and then estimate the heart rate. So, yeah, I can share some of the articles on the papers in case you guys are interested in this kind of topic. Very interesting. Okay. Okay, all right. Yeah, thank you, Stephanie. We think we don't have much time to continue for the discussion. So let's move on to the next presenter. Okay.
Is my screen visible, Professor?
Yes.
Okay. So good afternoon, everyone. Today I'll be presenting a paper on BioForce, a large biomedical image forensics dataset, which is written by the following authors, which is Ikram Sabir, Somarup Nandi, Wael Abdul Majid, sorry if I spelled that wrong, and Prem Natarajan. So this paper was initiated by USC Marina Del Rey, California, USA. So I'll be presenting this paper. So let's start with the motivation at the first place. So the motivation is like the first point is like there is no publicly available data set, as in particularly for forensics data set. And then the second motivation behind the second point for that is the critical manipulations such as given in the figure below, which is this one and this one. like these critical manipulations are really hard to detect. And as we can see that almost like out of 20,000 papers, like 760 papers at least contained one manipulation, which tells us the necessity, like that real, like the real basis behind this. So that 760 papers is approximately 3.8%. So now coming to the figure one, this is something that happened in this particular paper within document, which is, if we can see in the bottom right corner, this particular section has been copied and put onto this particular section of the other image. Now we can see, if you really want to, if you really look close, these three dots, if you can follow my cursor, these three dots are also similar over here. The same, like by the looks of it, it looks copied. And now something which happens across the documents, like we can see this particular like pattern of that particular blot, similar to this particular one in other papers. So this was done across the documents. So this was the real motivation behind this paper. And now the problem statement is like duplication. First of all, the duplication involves reusing part of images and generated by one experiment and misrepresent actually results for unrelated experiments. And then tampering of images involves pixel or patch level forgery, which is basically to hide unfavorable aspects of the image or to produce favorable results for that particular data set, for that particular experiment. And now the like my main focus point is like I found like the authors also mentioned that there is an estimated financial loss for $392,582 for each article that is retracted for these kind of manipulation tasks, which is a pretty huge number. So the main contribution from the authors are the Bioforce dataset. The manipulation, the Bioforce dataset, first of all, will be like in detail we will be seeing in the later slides. And then the manipulation detection tasks such as EDD, like external detection duplication, duplication detection, then IDD, that is internal duplication detection, and CSTD, which is cut short, CSTD. These will be again explained like in details in the later slides. And one of the major point that they concluded was that the standard computer vision models, when applied to these biomedical images, actually doesn't give those favorable results, like productive results, I would say. So now coming to the data set. The data set, like they actually on the superficial manner, these are the they got the documents, the figures, and all images. And on the on the deeper level, these microscopy images were again extracted from different kind of papers. The macroscopy images were also again extracted, and then the blot gel and the FACS. FACS is basically fluorescence activated cell sorting images. So now see, like after this data set, how they curated this data set, again, that will be coming in the later slide. But after curating the data set, they actually went ahead and checked like this, whether this data set is correct or not. For that, classifying these bioforce images using popular image classification techniques such as VGG, DenseNet, and ResNet. And we can see that train in the like they actually performed really well in the train and test images, like train and test data set. So now moving on to the approach to the problem, like how did they build that data set? So the first thing is that for the automated extraction, for this automated extraction, they actually use deep figures. They also tried different figure extractors, but deep figures had significantly better crop boundaries and worked really well on those all documents. For the croppings, now comes the like manual cropping. Now for this manual cropping step, they did it in two stages to avoid any kind of human error. The first stage was like cropping subfigures with a loose bounding box, which is basically followed by a then it is followed by a tight crop around images of interest, specifically those plots and all. And then they filtered out the synthetic computer synthetic generated images such as tables, bar plots, histograms, because that is beyond the scope of this paper. And now comes the manipulation detection task, which is cut sharp transition detection first, the internal duplication detection and the external duplication detection. So the cut sharp transition is cut it's like basically spliced or tampering the regions unlike spliced images, which is we can see over here. So like why they like use gamma corrections over here, because this is really difficult to analyze or understand where exactly the CSTD has happened. So this is the mask and this is the original image. So after that gamma corrections, we can actually see it really well. And now comes the like IDD. IDD is basically in single image. They, as we can see over here, these pink like the color alike boxes are containing the same image, but this is actually like if we rotate it like 180 degrees, we can actually see the same image over here. And again, similarly with these red boxes and the green boxes. And now the example of an EDD is an external, that's the same thing that I explained earlier on, that this particular section is copied and again pasted over here. So this is EDD. So I'll be a bit explaining the CSTD in a more detailed manner, which is basically like this blot or gel images actually do not show any clear distinction between the authentic background and spliced foreground, so making it difficult to identify that foreign patch. So now like for that reason, again, which I briefly explained, they used gamma correction to like differentiate between the light or dark like manipulated regions, so that manipulation can be seen easily. Now the IDD part, in the IDD is detection of internally repeated image or regions, which is again I explained briefly again, which is this part actually like it's more of like copy, move, forgery detection tasks where the source region is known and is also from the same image. So in this is pretty much like a bit easier than CSTD detection. So in IDD, the source region may or may not be from the same image, but the repeated regions may have been procured by manipulator from different image or documents. And now comes to the part of EDD, which is this one, is detection of near identical regions. Basically between images, duplicated regions may appear due to two reasons. One is copying, cropping two images with an overlap from a larger or original source. And the second was just like splicing, that is copy pasting a region from one image to other. So this is, which is basically this one, this is like splicing, like copying from one image to the another one, and when it's masked, we can see the similarity. So now moving on.
Sorry, Akash, sorry to interrupt. I just have a quick question about this slide. So for this IDD and EDD, right? So
Yes.
this is like a copy paste kind of procedure, right?
Yes.
So will that, result in obvious artifacts, right? For example, you look at figure 7.
Yes.
So there's a couple of identical pairs of bounding box, right?
Yes, exactly.
Different colors, right? Red had 2.
Yeah.
So if you just copy, like say, let's look at the red one, red box. You copy that to another place. Well, like, will that boundary will be very obvious, somehow like a blocking artifacts as compared to the original neighboring?
Actually, I didn't get that question. Can you like repeat that once more?
Yeah, here they are doing this kind of manipulation, right? So this is IDD, right? But my question is, will that be very easy to detect? Because, if you just copy one region, then paste to another region, then you will see some of the artifacts on the edge, right? Maybe.
Yeah, that's where like the next slide was coming on, like the potential challenges.
Okay, I see. Okay.
So if like, let me finish this slide up, and if that doubt is still there, I'll try to clear on my like knowledge level.
Okay.
So the first potential challenges in this biomedical research documents contains images that look similar, but the figure semantics indicates that they are not manipulated. And second semantics involve repeated portion of images that are magnified to highlight experimental results. And second, I'll get the figure over here. So this is the figure semantics that I was talking about. So now hold on a second, I'll just remove this. So if we can see this image where they actually have different colors of like different level of image pre-processed, and then they are combined it into one, which can actually like look like they have like did some like manipulation, but which is not. And again, over here, figure in this, the lower figure, if they are like, sometimes in some papers, they actually zoom in and show the portion where the important stuff happens. And that also can be one of the potential challenge for this kind of detection task. Maybe it can detect as, again, copied, but which is not actually. Now, coming on to the presence of these artifacts in biomedical images, which can actually create false positives matches for EDD and IDD task. Like suppose these lines, which actually looks like this side of the thing is copied to this side, but which is not. And these lines may be again taken as copy and move, like manipulation, which is again, it's like a false positive. And then comes the like these hard negatives. These are really difficult to detect, because blots and gel on a monotonous background are also very tough to differentiate. And then comes this image textures. Like biomedical images tends to have a plain or pattern like texture, with the exception of macroscopy images, which is basically like the bigger images. Those doesn't have that kind of like plain or pattern which look alike texture, I would say. This phenomena is particularly actuated, like this kind of thing is actually more into like the microscopy and the blot gel images. So yeah, that's yes, Professor. Does that clear some of the question or no?
Yeah.
Okay. So now moving on to like what kind of experiments they did. So they did different kind of experiments, like external duplication detection. They used numerous other algorithms to fetch the results, like SIFT, ORB, and BRIEF, and they used dense field Zernike movement and DMVN. Again, in internal duplication detection, they used similar kind of algorithms, but more into like polar cosine transform and Fourier Mellin transform and DCT-WT, and again Zernike movement and Busternet. And in cut short transition, they use two algorithms, which is one is Mantranet, and the other one that they used is a self-developed CNN, which is a basic CNN that they developed, and just run through the programs to check how, and that will be again discussed in the later slides. So like now, the results, in the results part, like if we see this in EDD, in the EDD part, we can see actually that the dense field Zernike movement have outperformed in the 3 out of 4 data set, kind of data set, and in the overall thing, actually DFZM has like outperformed the rest one by a significant margin. But for some reason in the DMVN data set, the blot gel, the DMVN method, the blot gel data set actually performs really well. Maybe that's something they have not explained why, but that may be because of the certain kind of algorithm that DMVN works. Now the results for the IDT, which is microscopy, in again we can see like dense field has really worked well, but in here the polar cosine transform actually has outperformed the Zernike movement. Again, other were not even close to the ones that they have achieved with DFPCT. So that actually infers a lot about DF, which I can again talk about in the conclusion part. Now it comes to the most interesting one, that is Mantranet. And the CNN baseline model that they have used, which we can see actually they have the base model of CNN have actually really came close to Mantranet, and which tells a lot that these standard computer vision models or the algorithms are not sufficed enough to do these kind of detection tasks. So now the conclusion, these automated and scalable biomedical forensics methods are really necessary to assist the reviewers, so that these kind of manipulation are detected earlier, and though huge financial losses that I mentioned in the previous previous slide, that was that huge figure of $392,000 is saved, because 760 papers per paper is $392,000 something dollars. If you multiply, that's a huge number, and that can save actually millions of dollars, and which can be put to right use for further research. And the Bioforce compromises a comprehensive range of images found in biomedical images document. The data set itself speaks for itself. The different kind of data they have, that is microscopy, macroscopy, and this wide range is actually a huge benefit to the society, which if put to use correctly can actually help the reviewers a lot. And the 3 manipulation detection tasks that they talked about are really nice, and which can be again with some more effort on those, they can be used really well. And again, what I discussed earlier on, that common computer vision algorithms are not enough. So we need more robust models to work. The strength of the papers are the authors has focused on the need to alleviate this kind of manipulation in medical image, which will help to produce much better research. And the manipulation detection tasks are really clear and easy to understand. And they uphold the fact that, again, same thing, strength, like standard computer vision model are not sufficed enough. It will reduce the burden. The one thing that I like really want to focus on, that it will actually reduce the burden from the reviewers, given that some software can be developed which can do the work for that the authors intended to do. The Bioforce dataset has a wide range of images. The weaknesses and the possible future work. The dataset has not yet been publicly released, and the model they have used were not the best in the field. Future work that can be done is the curated data set can be trained and tested on transformers, especially on the self-attention ones. That can be a work that they can look on, but I'm not sure whether that can help the results, or maybe some twist and tweakness are required in that. And the task that has been performed can be researched further for more improvements. So the overall rating I would rate is the paper 1 over 0, because they could I don't know whether due to time concerns or some reason they have not yet released the publicly the data set, when they actually said in the the paper to promote reproducibility. Our synthetic data generators and evaluation scripts will be released with the data set. So these are the references, and that's it from my side. Any questions or comments?
Okay, so yeah, thank you for the presentation. So I still don't quite get the motivation of this research and the data set. So
I'm going back
so
to that.
What is why do they care about this like a manipulated image? Is like common in this kind of medical kind of article, people are trying to fake the result. Like why do they care about this? This is like a common problem.
Yes, actually, if we take a deep look, I have seen some other if I'm allowed to hold on. Yeah, in this if we see in these 20,000 papers, actually they found 3.8% at least contain one manipulation, and that manipulation actually cost a lot to the publication, the ones who publicate those papers. And looking into that, sometimes they do these kind of manipulation techniques and to get favorable results and just to publish out a paper, and for which is a malpractice in a medical field. Because after all, somebody will take this method, implement into real life, and if that gives false negatives or false positives, God help that person who is getting tested by, who is going through that under that test, right? So they don't actually want someone to get hurt or something like that, because wrong identification of problems can lead to disastrous events. So for that reason, these are the small examples, but in a on a broader perspective, if we think something like brain tumor segmentation, or maybe liver lesion detection, these kind of things, if anyone does and gets really good results, so most of the junior researchers budding researchers like us will try to develop something based on that, and that's not a good place to start with.
Yeah, okay, yeah, I see. So yeah, I do hear some of the news, right? People fake the result in their article, maybe trying to get more funding or maybe promote their work. There are some ethical issues there. Yeah, I didn't see. Actually, there's here you are saying that 3.8% of these 20,000 papers they have. It's pretty serious, if this is the statistics.
Yes, Professor.
Yeah, because I see the harm, because it's not like computer science, right? We have the code; it's very easy to reproduce. For some of the biology experiment, then it may take years to reproduce the result, right? So if
Yes.
people tampering this kind of result, then it's going to be very harmful in this field.
Yes.
So I guess maybe I think for the publisher, they also may suffer some loss, right? Maybe loss.
Yes, that loss I
right?
stated over here, which is an astounding figure of $392,582. And this is not like a arbitrary number. If we like, can I get out of this presentation mode and go to the references over here? If we see this paper actually has this, like, I didn't go completely through this paper, but they also mentioned that we found that the papers retracted due to misconduct accounted for approximately $58 million in direct funding by the NIH between 1992 and 2012, and which is a huge number again. And each of these articles accounted for a mean of $392,582, like each article, and which is in direct cost, and other costs is costs like transportation and whatnot that is required for these kind of research, high level research, can be estimated around like $500,000.
Yeah.
So like looking at these numbers, this is actually something that is required by the reviewers, because again, the reviewers are just human beings, and they get loads and loads of paper every day to like review. So catching these kind of what should I say, this is still easier. The example of IDD, like we can like still do this, but catching these kind of like cut sharp transition detection, or like taking a layer of an image and putting into the other layer of the image, is really difficult to detect with human eye. So keeping all this in mind, these authors have actually proposed this paper.
Okay.
So yeah.
Okay. Yeah, I think this in general, this is very interesting problem, and has a great importance. But I think I'm now a little bit more concerned about now in the AI, machine learning, computer vision, right? So for example, the GPT-3, right, and OpenAI DALL-E, those kind of algorithm, they are able to generate a very realistic image, right? So they can, based on maybe just do simple copy paste, maybe it's not perfect, right? And maybe they can later using maybe GPT-3 or whatever to refine the outcome, right? To do minor tweaks to make a perfect manipulated image, right? That gonna be much difficult for this kind of AI algorithm to detect any of those kind of trait as the manipulation.
Yes.
So yeah, like you see, we can see that GAN can do a lot of generate a lot of realistic image. Right now there's some diffusion model can also even generate better result than GANs, right? And like a GPT-3, we can using text as an input to manipulate image whatever we want. So yeah, I think this is becoming more and more concerning. With this kind of technology, then it's become much easier to do this kind of misconduct. People attention to do so.
I think this will actually harm more in the biomedical field than equally it will be harming every field, but it will be more harmful for this biomedical field because this is related to someone's life, and these can be applied to realistic like real life too. So that is really something of concern. One thing I was actually going through, if I'm allowed to show, or the time is up maybe. Can I show that, or like?
Yeah.
So I was actually going through this Bioforce, like people who have cited this paper, which is not a lot. Only 2 people have cited this. The one that I actually went through, like these two papers, actually like shows the real concern. If somebody has the time to go through it, can go through, okay, what's the problem that they are facing. Again, see examples of original Western blot images selected and collected from dataset, and
Yeah.
these things actually are happening a lot because these have monotonous backgrounds, and detecting them is
Yeah.
really hard if it's copied. So like again, the one you were saying, sir, the StyleGAN 2, like replicating all those images is really concerning factor. And over here in this pair, like PubMed retraction, we can actually see how many papers that have been retracted due to these kind of manipulation technique.
Yeah.
So, and this is what the top 11 publisher have 3,405 withdrawal articles, 70.3%. So that's a huge number in 1,165 journals. So these were the things that I was relating with. Yeah, that's it on from my side.
Okay. So I guess this bears some similarity as deep fake, right? We talk about deep fake can generate those realistic image. So maybe I think for counter this, you know, you guys can look into deep fake as some of the recent approach, like how can you?
Yes, they actually mentioned in the
Yeah.
articles itself, like deep
Yeah.
fake is actually, and from that only they used this particular method. Yeah, deep figures to like, sorry, not related to this. They said these deep fakes, and they have other methods to detect those deep fakes, which was talked about in the related work. But since it was not related to this particular much related, so I didn't feel like putting into the.
Yeah. Okay. Okay, great. So I think we are over time. So I'll do you guys have any questions? Okay. So if not, we're gonna end here. So I think this is a very interesting topic. Yeah, I think maybe if you guys are interested and you can look into this, there's maybe a lot of market value here. Okay. Okay, all right. Yeah, thank you guys. For the next week lecture, I'll just give you some of the guidelines of the final presentation and do the like a final summary of the course. Okay. Okay. All right. Thank you guys, and I'll talk to you next week. All right. Bye.